Hello fellow skeptics, I'm Luther Name, and this is the 21st video in an arc of 20 videos addressing the topic, is there something wrong with physics? If so, can it be fixed? Now, I really concluded with the arc in the last video, the 20th video. This is a wrap-up, but based on some comments that were made, I decided I really needed to add an additional video. So this is going to be at least two videos, this video and the next one, addressing and I call it an arc, that started at Newtonian and pre-Newtonian physics and addressed the issue, the topic of these videos. Is there something wrong with physics? The organization was such that you start at the beginning, you teach from first principles, looking to see what the first principles really were, and move forward up into Einstein's relativity theories. It's like the progression that exists within a textbook. You start with basics at a certain level, and then you move through adding complexity, both in terms of the topics, the scenarios that you're addressing, and the mathematics that are used to approach solutions to the mechanics, in this case Newtonian mechanics, dynamics, and the course then ends at a particular point where ostensibly the student has a certain level of expertise that allows them then to go to the next course. The next course begins the process again, only at a higher level, and you proceed that way. So you have a series of courses that each progressively introduce the student to more mathematics and more complex ideas. And what I'm going to do is address two separate issues in these next couple of videos. The first one is what I expected in the way of a critique of the material that I did present. There were places where I expected pushback, and I was prepared to address that pushback. In posting the summary, there were a lot of comments that there hadn't been before, and there were apparently a lot of people who had just popped in for some reason. That particular video had attracted attention, and so there were a lot of comments. For a while I tried to answer some of them, and then I realized that I couldn't do that for a variety of reasons, and I'll get into that. But I realized also I had made a bit of a mistake. And that mistake was that at the beginning of each of the videos in this series, I had not specified that this was an arc. Much like in a course where you start at the beginning, you become increasingly more detailed and deal with more complex issues until at the end where you have finally put together the story and supplied all the information that needed in order to come to a reasonable conclusion. People who jumped in the middle oftentimes said, well, why are you doing this? And it became clear that I really should have alerted people that if you're not willing to go back to the beginning and deal with this thing as an arc, then you were wasting your time, and any comments you made in the interim were a waste of everybody's time, including mine. There were some good comments, and for those of you whom I didn't get to them, I apologize, but I just felt that it was not a reasonable use of my time and your time for me to deal with it. For instance, somebody would say, what do you think about this particular theory? I never heard of it. I haven't heard of all these obscure theories from obscure physicists in academia, and as it turned out, I don't really care, because they're working from the same source material every other physicist is, and they don't have the complete source material, so whatever they're talking about by definition is going to be incomplete, because they're trying to compete in some fashion by either modifying or adding on to what we know of modern physics, and modern physics is riddled with errors. They can be traced all the way back to Newton's time and pre-Newtonian physics. So what I wanted to do was kind of set the record straight, because these comments got me thinking about a variety of things. and that were probably worth talking about. I spent a lot of time looking at various YouTube videos and articles written by people who are spokespersons, often self-appointed, of the physics community. Some are very good. Sabine Hausfelder is a very good one. I don't think that she is right all the time, but she's got that particular detailed attitude of getting to the details. And many of the things she talks about, I agree with the conclusions she comes to. But she's willing to broach subjects and ideas that many of them aren't. Some of them are just talking heads. They just talk. And they're regurgitators. I don't know that they've ever done anything really uniquely creative or even correct in what they've done. As I've looked at them, the more popular ones, they're monetizing what they're doing. They're talking heads. I just get nothing from listening to what they're saying. On the other hand, there are some that are only periodic contributors that have done some really interesting stuff, and they have some interesting things to say. So I can't dismiss them. And many people are beginning to express great reservations about the status of physics at this point. Sean Carroll, whom I've mentioned before, is one. Sabine Hausfelder has also made these same comments and quoting other people. And she gets invited to various group meetings, apparently hasn't alienated herself, and there seems to be a lot of consensus that she's right. In the last 40 years, something's gone wrong. Not only in academic physics, but also in academia. And I think a growing number of people are of that particular opinion. I certainly am. Because I saw when I was beginning my career that there was something beginning to skew out of what I consider to be the trajectory of what I was led to believe was proper and productive within academic physics while I was in academic physics. So there are a couple of areas where I thought there would be pushback. One of them was the very fundamental statement by Newton as to how he envisioned the interaction between two objects, gravitational interaction. And using that as a scenario, you can set up an equation that describes how that interaction might occur across the volumes. He set it up all right in the sense that his observations have not been open to question, or as he set it up, nobody has questioned whether or not his concept of how gravitational or electrical interactions occurred between two objects. But what nobody has questioned is the way he solved the problem. So the issue wasn't so much the scenario that he set up. It wasn't so much even the mathematical model that he developed to describe that particular interaction scenario. It's the fact that he made an approximation associated with how to solve it. That's all he could do. I mean, he couldn't solve it any other way. And in fact, up until the modern computer era, it was almost impossible to solve these things directly. So the issue wasn't the scenario that Newton established. It isn't even the way he solved the problem, but he solved it without recognizing that he made a simplification. In fact, nobody knew that was a simplification. And so they followed that script for 300 years, and until the modern computer era, where you could use commercial software and desktop computers to basically solve the exact problem, you couldn't solve it. So in that particular sense, the pushback would have been pretty minor. Anybody who wanted to argue against the model that Newton had set up, or even any of the scenarios, would have been pushing against established practice. Now, that doesn't hold true for the second area of pushback, and that had to do with the area on inertial versus non-inertial propagation. Now, photons are taken, or most people believe that their mass is so small, we haven't even been able to measure that mass. We say it's less than a certain amount. What we measure is momentum. And from the perspective of momentum, momentum is mass times velocity. And so the velocity is pegged at c, plus or minus a little bit. There's some discussion as to whether or not the speed of light, in fact, is constant, but it certainly doesn't appear to vary that much if there is variability in it. So with the velocity of c for the apparent or pseudo mass, as they call it, of the photon, what you have is a very minuscule mass that allows it to have the momentum that it does exhibit. So the issue here is inertial versus non-inertial, and that has to do with mass or no mass. Now, I thought there might be some pushback in terms of the way I identified the non-inertial propagation, and the fact that almost all the models for the scenarios that have been depicted for supporting special relativity in particular have been misanalyzed. They missed the physics between the inertial and non-inertial propagation. I thought for sure that somebody would raise that particular issue, but what happens is that if you take the photon mass to be negligibly small, then what happens is that with the high speed, the velocity of light, it's essentially a straight line, and without any momentum in the direction of propagation of the emitting source. An atom moving in this direction, emitting a photon at right angles, that photon has its origin at the instant it's emitted, and it's anchored, so to speak, in space at that particular point. For an inertial mass, on the other hand, say like firing a gun from a moving platform, what happens is the projectile has that component of momentum along the direction of motion of the object, because it has mass. If it's massless, then if we're massless, it would just go straight, and the point of origin would lag behind the retreating or moving origin that continues to move where the platform continues to move, but the origin of the emission, the firing of the weapon, or the emission of a photon stays locked in a particular spatial coordinate. So I thought there might be a little pushback there, but there wasn't. Frankly, it wouldn't have made any difference. The real issue was that you can develop these scenarios, but Einstein in special relativity in particular never developed these particular scenarios correctly, and then he never tried to solve them. At least with Newton, we set up the scenarios and then we tried to solve it, and we came up with approximations. But even with the full knowledge that photons propagate inertially, apparatus like the Michelson-Morley interferometer or any other ferrometer, they're analyzing correctly, treating the photon propagation essentially as if it were inertial. And so I analyzed the various scenarios using that non-inertial aspect of the propagation. And what that does is it negates all of the so-called scenarios and explanations that we have tended to dumb down for people who are not literate in calculus or advanced mathematics, but are just essentially entry level and know algebra, may know a little may know a little elementary calculus, but we don't need to use it. So with that regard, that is how the whole issue of the descriptions and the explanations came about, and that's really all I'm going to say about that. I gave some thought to how you might practically measure something like the existence or non-existence of an inertial component to photon propagation. First place I looked was at some advanced technology that's currently well worked out and very effective. It's an elegant technology. It's called synthetic aperture radar. If you look at the way it works, an aircraft is flying along, it emits a radar beam out at right angles to the trajectory of the aircraft. The radiation goes out in the footprint. Part of the footprint hits an object on the ground. The radiation is scattered off of that and comes back to the aircraft, which is continued on along its trajectory. Now, you can calculate the time it takes for the radiation to get to the target, so you can get distance to the target. Because the aircraft is moving perpendicular and the target is typically stationary, there's no effect of the aberration and frequency shift. So the radiation that comes off then is reflected and goes to the aircraft, and when it's redetected by the aircraft, where the effect is of the antenna having been dragged in this dimension to become very large so that you have very fine resolution in that particular dimension. And when you build up a picture, the way they record the data that comes back to the radar, what you have then is strips of very high resolution imagery that you can collect, and that was one of the first, in fact it was probably the first practical application of holography, which fortuitously, with the invention of the laser at the same time, made the signal processing for these aircraft, synthetic aperture radars, much more effective and quick and accurate. So what happens though is, if you have an inertial component, now you have a frequency shift. You have a frequency shift because the aircraft is moving when it detects the radiation, but now you have, because if there's an inertial effect, you would have a component of momentum along the direction of the aircraft trajectory, so there'd be a frequency shift of the emitted radiation. This is going back to the Doppler and aberration effects associated with special relativity. Now the radiation is reflected, but it's already been upshifted slightly because of the motion of the aircraft, and then it's reflected and comes back, and there's another Doppler shift because the aircraft is now moving away from that point, but now it's different. It's not canceled out, and so there's a differential frequency shift. So you've got a number of effects occurring when you try and use a practical application. The reason for the practical application was that oftentimes organizations that are using, have perfected and are using these advanced systems with signal processing collect a lot of data, and then they store it. Unfortunately, a lot of times they throw it away too. In the case of NASA, they collect everything, and of course they were the masters, the early masters of signal processing, communication signal processing. And in a fortuitous example, maybe 20 some years ago, they resurrected the data that had been collected, communication data, with the Pioneer spacecraft. This had been stored. Somebody retrieved it after 20 years and analyzed it, and they thought for a while that they picked up on an anomaly and thought it was associated with general relativity. Well, in an indirect sense it was, but it was actually part of the Doppler aberration effect that they didn't account for. But they picked up an anomaly, and they made some measurements, and they resurrected the data that they could pull from this old data, signal process, communication information, and thought they stumbled across another way of verifying certain elements of general relativity. But they hadn't, and when they completed their analysis decades ago and put it to bed, they thought they had discovered the source of the anomaly. Well, they had maybe a piece of it, but not the whole thing, because they had left out fairly substantial chunks of the analysis, namely that associated with the Doppler and aberration in the radiation. But the point is that this data is collected, oftentimes without a full knowledge of exactly what it might be used for, and oftentimes it's just stored and forgotten and purged after some period of time. So I thought about a few of the scenarios we might use to find out, or maybe determine, whether there could be an inertial component. of some sort to the photon propagation. However, because the aircraft motion is at best a kilometer a second, the beta, which is the velocity over the speed of light, is so incredibly small that we can't measure these kinds of effects very well. We can, if we get down into very good sources in the radio wave and long wavelength microwave region. But if we were to use optical radiation, we can't get close to that kind of resolution. The best way to get a high speed would be to use something, perhaps like an ion accelerator, and to stimulate the emission of photons and to create a geometry much like some of the interferometers that have been discussed before, and make your measurement where you now have a velocity of the emitter being a large fraction of the speed of light, so that you get very large effects. We could very easily do this almost any university, and almost as a tabletop experiment kind of thing. We used to know a lot about accelerating electrons and ions with through a potential. Van de Graaff generators is an example of that. But as those imaging devices like televisions, and as these other apparatus like the Van de Graaff generators are retired and no longer in use, the expertise to be able to develop these kinds of measurement systems would require coming back up a learning curve and exactly what to do with these technologies. But it could be done. But so there are ways of being able to determine using a better insight as to whether or not the photon has mass. In this case, you take advantage of the fact that you understand that there is a difference between inertial and non-inertial propagation with respect to photons. So that's really all I'm going to say about this, but we still don't know. We still have universities and academics performing some of these experiments to try and determine if the photon has a mass or a measurable mass. And just like the conjectures that the speed of light may be variable, they're conjectures. There's no sound or convincing proof at this point. But then, given the fact that nobody understood how exactly to analyze the various interferometric effects with respect to the inertial versus non-inertial, you'd have to say that maybe there's an opportunity here for somebody to actually set up an apparatus, correctly model what's happening, and then to be able to do the experiment itself. It'd be a hard experiment, but it would be well worthwhile. There are many experiments that are worthwhile doing that are very difficult, but they're just to prove a point. There's no long-lasting spin-off associated with most of these. An example is the Mossbauer effect, which I thought was an elegant experiment and a set of measurements, proved a point, and won the Nobel Prize for Mossbauer. But there are very limited practical applications to the Mossbauer effect. So at this particular point, there's really nothing more to be said. The pushback that I expected didn't occur. I had thought about it, and so what I'm going to do is put the rest of the discussion about the arc and the pushback that I expected behind me, and move on to the 20-second video, the next video, where I discuss my take in terms of how do we fix it, what's broken. We can fix the physics, but can we fix the system and the institutions associated with why physics got broken in the first place? We've ascertained through this arc that there are things wrong. There may be other things wrong, but I identified some things wrong. And these things have rippled from Newton's time through 300 years, well actually 200 years into relativity, and they've corrupted our approach to modern physics. And now we need to fix the system, fix physics, so to speak. But can we do that? That's the topic of the next video. I'm Luther Name. Leave some comments, and I'll talk to you shortly. I know, quit calling me shortly.